All right, I'm gonna just talk about something really quick off the cuff here, which is gonna help us a lot with two-dimensional arrays. So, and that's matrix multiplication, and it's something that NumPy was designed to handle. So you can also think of a two-dimensional array which has the same number of elements for each row as a matrix. So in particular, if I say, x is equal to mp.random.rand 3, 4, we say this is a 3 by 4 matrix. So let me just print it out. Which I'm going to call it A. I don't know. I'm going to prefer capital A right now. All right, so I just made a 3 by 4 two-dimensional array, but we can think of this like a matrix. All right. So let me make another matrix. Actually, in the history of NumPy, they started off with a different data type for a matrix. And then that was deprecated and everything became an array, because an array is actually more general. You can go up beyond 2 dimensions. You could have a 3-dimensional array, which represents a volume, or a 4-dimensional array, which represents a hypervolume. But we're going to be focused on these 2-dimensional arrays because they represent spectrograms, and we're going to be doing a lot of things to spectrograms. And so I'm going to introduce matrix operations as a way to do things quickly to help us. So let me make another one, which is maybe a 4 by 2 matrix. I'll call it B. Okay, so this one has 4 rows and 2 columns. So I can define matrix multiplication of an m by n matrix A by an let me say this. No, n by k matrix A by a k by n matrix B as the product it's AB, it's written as A times B, where AB at row I, column J, is equal to the dot product of, I guess I'll write this in Python notation, the dot product of the ith row of A with the jth column of B. Okay, so let me write that out in words too. So the element ABIJ is the dot product of the ith row of A and the jth column of B. All right? So if that's the case, if I'm taking rows of A and columns of B and doing the dot product, well, the rows of A must have the same number of elements as the columns of B. That's why I see that the second dimension of my first matrix is K, and that's also the first dimension of the second matrix. So each row has K elements in the first matrix. So when I pull out a row, it's got K elements. Each column in B has K elements. And I do the dot product. So I could define this in a very naive way as saying, I'll write a function def matrix mul. I could say that my result is, so let me get all these. N is equal to a dot shape 0, k is equal to a dot shape 1. I'm going to assert that b dot shape 0 is k. This will crash this assert. If this Boolean statement fails, it'll crash the code. So it's making sure that the B has columns which are the same length as the rows in A. Okay, and then I could say M is equal to B dot shape 1. So then AB is equal to MP dot zeros. Sorry, let me make this M and let me make this N. Oops. Make this N. Okay, MN. And then I could just do the following. So I'm going to loop through all the rows. I'm going to loop through all the rows in AB. I'm going to loop through all the columns in AB. I know there's M rows and N columns. So yes, product AB I should write which is an M by N matrix. All right. So M rows and columns in the product AB. And I say AB at row I, column J, would be the sum of the dot product of the ith row of A and the jth column of B. All right, so I'll return that. So that's how you could do matrix multiplication in NumPy. So let me just do that. AB is equal to matrix mul AB. Let's just print. Okay. So I started, in this example, I started with a 3 by 4 matrix, multiplied it by 4 by 2, so I should end up with a 3 by 2, and I do. So the dimensions work out. Matrix multiplication is not commutative. What it means is A times B is not the same as B times A. In fact, this will throw an error. If I try to multiply a 4 by 2 matrix by a 3 by 4, well, those inner dimensions don't match up. I don't have the same number of columns in my first element as I do rows in the second one. So A times B is not B times A. So you got to be careful about that. But anyway, that is that. Okay. But this is not the way that you would do matrix multiplication in NumPy. NumPy was, as I said, was designed to do matrix multiplication. So there's already a built-in method for this, and it's dot. So I'll say AB2 is equal to np dot AB. So dot actually stands for dot product, but the generalized dot product is this matrix multiplication. So we're doing a bunch of dot products here. Let me just print this out and make sure it's the same thing. And it is, okay. So actually, if you look at this, I just want to make a note for those in algorithms. This is a cubic algorithm for computing matrix multiplication. Because it actually goes through, well, if M and N are about equal. You loop through M, you loop through M again for each one of those. And then for each one of those, you have to do a sum over N elements. So that's N times N times N. So it's actually a cubic algorithm. You could do a little bit better than this, theoretically, but not much better. So anyway. All right, so that's matrix multiplication. Now, one of the things we can do with matrix multiplication is, I'll show you a quick example with the spectrogram. So let me go back and grab some of the code where I was computing the spectrogram on beetles. So, all right, so I've got this SDB here. Let me plot that real quick. So let me say that, all right, so I could think of this spectrogram as, let me print the shape. So the shape is, okay, so I took, my window length was 4096. So the non-redundant frequencies, there are 2049 of them, and there's 431 time windows. So I can think of a spectrogram actually as a matrix with 2049 rows. Okay, let's say that I wanted to extract some information from the spectrogram. So I wanted to look through each column and say, how much energy is there around bin 750 in frequency? So I can make something called a bump function. So I'll say B of X is equal to E to the negative X minus center squared over sigma squared. Okay, so actually this is 2 parameters. So I'll say bump, it's got 2 parameters, center and sigma. All right, so this is called a bump function. Let me just define it and we'll look at it. So let's say C is equal to 750. I wanted this to be centered at 750. I'll make sigma 50 bins. And so I'll say B is equal to np.exp negative np.arange sdb.shape 0 minus C squared over sigma squared. So let me plot this. Whoops, that doesn't look quite right. C is 750. Whoops, I meant to have the minus C on the outside there. So it's np.arange of that. Okay, there we go. There we go. All right. So now I have a bump that's centered at 750. If I take the dot product of this bump with a column, I'm only going to pull out stuff that's around 750. So I could do that in a loop. I could say I guess I could say y is equal to np.zeros sdb.shape1. I'll loop through all the columns, and I will do the dot product of the bump. So I'll say y index j is equal to sdb's column j dot product with this bump. So that'd be a sum of all the products. Oops, lowercase y. And so anyway, this gives me the energy around 750 hertz at every column. Okay, so I could do that with a loop. But I could also do this with matrix multiplication, because I'm just doing a bunch of dot products, and that's all matrix multiplication is. So if I set up the right shape, I can do a matrix multiplication. So SDB is 2049 times 431. So let me set up a 1. So let's set up, so we got SDB is 2049 by 431 times 431. So let's set up a matrix for the bump that's just a column matrix. So what this is going to look like, which is, so it only has, or no, actually let's make it a row matrix, So it just says a single row. So it'll be 1 by 2049. And we can do that multiplication. So if I multiply on the left 1 by 2049 by 2049 by 431, I should get a result of 1 by 431. So let me set this up. So I'll say bump is equal to mp.zeros. It should be 1 by 2049. So I'll say 1 and then sdb.shape 0. Maybe I'll call this capital B for bump, because we already have this lowercase bump. And so I'll just then make the first and only row of bump be the bump that I created. I might as well just copy this equation down here. Oh, I called it B. Okay. So there isn't a name collision here, but just for clarity, I will say this. All right, so the first and only row is going to be that bump of this matrix. Now I can compute a matrix multiplication to get this y. So I'll say y is, it's going to be the product of bump dot dot. So, and actually let me write it like I did before. mp dot dot bump SDB. And actually, so y is going to be a two-dimensional array. 1 by 431. To make this back to a one-dimensional array, I have to say flatten. Okay. So now let me plot this and just show you that we get the same thing. And I didn't have to do a loop, because I used the fact that when I do a matrix multiplication of this thing, it's going to take the dot product of this, which I'm expressing as a row, with every column of this. So matrix multiplication gets us to do that. And so we're going to build on this to do a lot of other tasks. All right, so that's it for now.